Good day, everyone. So good morning, good afternoon, good night, depending where in the world that you are connecting to the next edition of CEDA Virtual Distinguished Lecture Series. I believe this is the last one in this year. So for the next month, December, you are very welcome to attend the Design Automation Conference, whether physically or virtually. And there are CEDA invited lectures there as well. Today, it's our pleasure to have the distinguished lecture on hardware-supported cybersecurity for Internet of Things by Professor Yier from University of Florida. So I just give a short introduction. So he is the endowed IoT term professor in the Warren Nelms Institute for Connected World and also an associate professor in Department of Electrical and Computer Engineering in the University of Florida. Before joining UF, he was the assistant professor at the University of Central Florida. He received his PhD in electrical engineering in 2012 from Yale University after getting his bachelor and master degrees in electrical engineering from Zhejiang University in 2005 and 2007. His research focused on the areas of embedded system design and security, trusted hardware intelligent property cores, and hardware-software co-design of model computing systems. So he's currently focusing on the design and security analysis of Internet of Things and wearable devices with particular emphasis on information integrity and privacy protection in IoT era. So without further ado, I leave the floor to Yier to present this talk. So for the questions, you can basically during the presentation, you can put it in the Q&A. So please do not use the chat, use the Q&A for the questions. And after the presentation, Yier will answer your questions as well. So Yier, the floor is yours.
Thanks for the introduction. So welcome to my talk. So for some of you may notice that I put a few affiliations here. I'm currently actually a courtesy professor at UF, pursuing some industrial opportunities. For example, one of them is we call the silicon assurance. We're trying to help commercialize some of the hardware security techniques so that it can really help. I mean, I know we publishing paper, it already helped a lot. But if we can deliver tools, it will be even better. So my talk is about the hardware supported cybersecurity for IoT. So first, what is IoT? I think after so many years of development of IoT and the kind of like the education about how IoT really changed our life, things are become more and more popular, I would say. And not just IoT, it's also CPS, we call the cyber physical system. So now almost all the industrial system, people are thinking to convert them into the IoT style, like a vehicle. Now we are talking about smart vehicle. Smart electric vehicle is really a computer plus 4 tires. So this change is something that we do not really expected only a few years ago, because we think that a vehicle or smart vehicle is an area that with a very high bar, but the companies around the globe, like Tesla, prove that no, it's not, it's a computer. Definitely something more than a computer. And for power grid, for smart transportation system. So this is kind of like prevailingly available. So now the question becomes, if we try to model an IoT or CPS, because as a cybersecurity researcher, we always want to first know what is our target before we try to protect it. So the first thing is that IoT is everywhere. So it's kind of a bit challenging to define what an IoT is. We cannot simply say it's IoT, it's everything. Some company even name it as IoE, Internet of Everything. So what I conclude here, IoT is a framework, a system that at the bottom line, we see some small devices, right? And then we have a cloud to support all this communication. And we also have applications through our cell phone. And these IoT are deployed in almost everywhere in our lives. So this is everything putting together, software, hardware, they become IoT. Because it's a so broad definition, and the reality is that it is broad, then from the cybersecurity perspective, the attack surface also grow exponentially. So this is a simple summary of what kind of like IoT attack we may encounter. From application layer, middleware layer, network layer, perception layer, these are all something that the attackers can leverage. And even worse, the attackers, we always say that attackers are much smarter, so and more patient. So they may combine all different layers of attack. So one very, I would say, recent and timely example, if you are working on AI and you are working on smart vehicle, people are trying to attack the sensors and making something appear or making something disappear. The sensor itself is an IoT device. And through that, they may break into the service, the vehicle service, to break the vehicle or to kind of like accelerate the vehicle. So these are all, I would say, that the attacker surface. And with all this surface, I have to say that attackers never wait until we fix all these issues. They see the table also, and they quickly put it into practice, much faster than we are. So we have so many IoT attackers, and this is only a list of a few we called the Mirai style IoT bots style attack. We have more than that, but these are only a few examples that they show you why IoT attacks are different. So people are thinking the interesting or the very like a reasonable question. We have been dealing with system security for so many years. Can we just leverage existing cyber security solutions? And why IoT attack become different? One key difference is the volume. We have so many IoT devices, so that if we compromise one, we may be able, and they're all connected in the internet. And if we compromise one, we may using the very same methodology to compromise the rest. If we only compromise 1%, it could be 10,000 or even 100,000. And you suddenly can control a network of devices, which you can launch further attack through them. So this is the real impact. And most of the example here are on commercial device. The industrial device is the same thing. There actually a news in a couple years ago. The news reads the title here, US escalates online attack on Russia's power grid. So the question becomes, the keyword here is escalates, which means that it's happening all the time. Just to sometimes be more tense, sometimes become less tense. So we actually are, when we read this story, we're asking, so what about the situation? Is Russia also attacking the US power grid or not? So what happened to the whole power grid? So we actually take a few, I would say, a few days to collect information. We realize that, yes, it's happening all the time. Only from 2010 to 2020, US had launched numerous attacks on Russia's CPS system. So do Russia. So these are all the examples that we read from the newsletters, and there are definitely a lot that we do not really see from the public domain, which I do not have any access to. The question becomes, this is something that is happening, it's real. So now the question becomes how we can fix them. So there are many solutions. For the IoT botnet, we have honeypot, IoT pod. For the IoT level, like sensor level attack, we have some filters. So there are a lot of solutions. I have to say that we are developing various solutions from hardware, software level, like the attack trying to attack us. So what I want to introduce today is we call the hardware assistant solutions. Why hardware assist? So let's take a look at this IoT design and this, the overall IoT framework again. So what is hardware assist here? It's actually this line. And there are also a lot of like IoT virtualization, a lot of solutions. So in this talk, I emphasize the hardware assisted solution. The main reason is while the IoT system become more and more complex, which means that attackers, they see the IoT device is not like decades ago that is only very simple ECU. It could be an ARM core, a very complex ARM A core. It's very complex. It can run in the whole OS. So, but at the same time, the resource is not that much to deploy all the defense. Like in cloud, we may have very sophisticated defense system, but they may not be deployed on IoT system. So when we have the imbalance that the attack surface become large, the defense surface are shrinking, we always realize that a hardware-assisted solution is more efficient. But hardware-assisted solution have the drawback that you need to change the hardware, or even worse, you need to first know the hardware. And many people are working on cyber area, being software development for years. They never know that, okay, for them, hardware is a virtual layer that it's just to run instructions without doing anything else. But if we do know the hardware, we leverage the hardware to perform some assistance to the cybersecurity solution, we will see a lot of benefits. In fact, very simple hardware change can do a lot that some software cannot perform. So I don't want to dig deep on that. I just want to focus on this talk is hardware assisted cybersecurity solution for IoT device. If you are thinking about other topic like trust zone, SGX, these are all other examples that you will be more interested to explore if you really want to learn more about the hardware assisted solution. So in this talk, I will quickly go through 3 of our techniques. One is the Hafix, we call it defending runtime attack. Runtime attack is still a very hot topic, although a bit less hot than a few years ago. But IoT attestation and authentication become very hot topic recently. So I will introduce some work in this area. So first, Hafix and Hafix++. So many of you already know this code injection attack, which means that when you have this program and leveraging some like buffer overflow style vulnerability, the adversary can inject some malicious code and corrupt the code pointer so that this block D, instead of jump to block F, it will jump to the adverse, the maliciously inserted code. And then we call it the code injection attack. And this problem have been, I would say, perfectly solved by DEP. Again, interestingly, DEP itself is a hardware solution. It adding 1 bit on our memory to indicate whether the memory is writable or readable. So the DEP enables that some area can only be read, cannot be write. But attackers quickly come up a code reuse attack. Instead of insert some code, inject some code, they compromise the some code pointer and ask it to jump to other area, other blocks. So by reshuffling of these basic blocks, eventually the attacker build a malicious program. So this is called the code reuse attack. So it's happening, I skip this, it's happening in the last few decades, and many solutions have been proposed. Overall, they have 2 categories, one called randomization, one called control flow integrity. The idea is that if you want to compromise the code, you need to know where to jump to, because you need to chain them together. For the randomization, the idea is that if I can keep on adding some random, put the code blocks into some random addresses, then attackers may not find the address, so they cannot chain them together. Another solution is control flow integrity. They want to show that if we can always test that one block can only jump to the other block, not some block else, then if this can be compromised, then this malicious jump will be detected. So we all know the randomization solution is less secure, but low cost. The control flow integrity is more secure, but a high cost. So for the IoT device, we want to have low cost, but high performance. So how to do that? So eventually we need to apply, if we really want to achieve high security, the CFI is definitely the control flow integrity solution, is definitely the option. So if we look into the CFI solution, eventually we needed to check 3 types of instructions: return, jump, and the calls. Right? So we need to make sure that these all returns are returned to the valid address, or jumps are jumped to the valid target address. And all indirect calls also target address that they are valid and not some arbitrary position to chain these blocks together. So we need to eventually protect these 3 types of instructions. And we do have software solution, which means that every time we see those instructions, we have another block to deal with them, to make sure they do the benign behavior. But if we can come up with new instructions, so now we come up with this key idea, the hardware assisted solution, which means that if we can come up with the new instruction to check the instruction, the overall cost to enforce the control flow integrity will be lowered significantly, right? So with that said, whenever you want to add the instruction, you need to have the, we call it state machine register. So in order to achieve that, our solution is that we have a 32-bit CFI state machine register. And each of them, we can even have some reserved bit because we don't really need to use all of them. So we can perform the CFI check, CFI flag, CFI fault, CFI finite state machine states. So we have all of them, and to map into this register, because these are new register, the original compiler, the original instructions have no idea that they exist. And to modify these register values and to leverage this register value, so we needed to add new instructions. So here we add 5 instructions: CFI branch, CFI return, CFI PRC procedure, and the CFI PRJ and CFI check. Right. So these CFI instructions can help combined with the CFI state machine register. Together, they can perform a goal. Sounds very simple. Goal is make sure each call return here, each return, each jump, each call, they are doing the benign behavior. They are not jump maliciously. Right. So why hardware? As I mentioned, this is the only option that can balance the efficiency and the security. Definitely, they have the drawback, as I will mention. Change hardware is not always easy for, especially for software programmers. But we do achieve high security with very low overhead. So as I mentioned here, that we can achieve a very precise CFI policy enforcement with less than 3% overhead. And we are supporting shared library, we are supporting multitasking. And the CFI and the non-CFI code on the same platform, which means that we are supporting the legacy code. The legacy code without the CFI instruction can still run on the system. And some data shows here that on average, it's 1 to 2% performance overhead and around like 13% of increased code size. So this is the first time we see that the power of hardware-assisted solution. And before I talk to some other solution, I want to emphasize one thing is, when we started working on this area, it's a few years ago, and we trying to introduce this topic, this work. People are saying that no one will change hardware for you. Why? Because Intel will not change their instructions for you. ARM will not change their instructions for you, because they are very strict. They will not just adding a few instructions for some specific purpose, right? But the funny thing is that even at that time, we quickly realized that Intel already have the CET. The CET is some new instructions to perform the backend, the CFI enforcement. And also they supporting the shared library and multitasking. Right. As I showed here, that our Hafix and Hafix Plus have all these kind of like the performance compared with existing solutions. So at that time, we already know that even company like Intel, they will add new instructions to achieve the security purpose. And rolling forward, at this moment, with RISC-V being so popular, no one would ask the same question again, because the RISC-V really like liberate our imagination. I would say in the last 5 years, we see a lot more like hardware-assisted solutions happening. They're all being powered by the RISC-V core, because now we can safely claim that, see, we do have the hardware-assisted solution, and we can change the core, and we can even fabricate the RISC-V core. So we are one of those groups. So with that said, we're moving forward to the HM and the Lahel topic. They are trying to solve another issue, not to protect the runtime integrity, but also we call it the platform integrity or the attestation. What is the platform integrity? We normally have two parties or two entities. One is the trusted one, one is untrusted. But we want to make sure this untrusted one is something that is still running in the trusted status. It's very simple in the IoT domain. The trusted party is the server, and the entity under testing, under attestation is an IoT device deployed at somewhere, maybe in the environment that attacker can easily access to it. So now we are asking the question that, will the attacker already have the physical access and change the code? So we would, can we still trust the information collected from that device? So what we do is that we send in some integrity verification, and then we get some remote attestation, and eventually we can ensure that the entity is still in the trusted, or is still in the trusted mode, or is still something we can trust. But almost all existing solutions are like software. They assume that software attacks. So, but this is not valid anymore in the IoT domain, because many of the IoT devices, they are deployed, or we sometimes call them edge devices. They are deployed at edge. Attacker can easily access them. So some kind of like a physical attack is possible. So we are proposing solution to say that, what if physical attack is happening? What shall we do, right? So for the so this is just a high level introduction for the platform integrity. Now let's dig a little bit deep we call the remote attestation. The remote attestation is we have two entities. One is we call the verifier, is someone we trusted or something we trusted. And we have the prover is untrusted. The prover have to prove itself before we trust it. So what we do is that we normally have some software running on the edge device, IoT device. And our goal is we want to make sure that this software is still the same software. It's not being compromised. So what we do is that we send some challenge, and we normally have some attester is a hardware anchor there. This anchor is read-only, you cannot really change it. So we ask the anchor to test the integrity of the software. A very basic solution is using hash to hash the code and sending the authentic report back, right? Then this report will be compared with this measurement database. If the value match the database, then we trust it. If the value does not match the database, we do not trust it. But now the question here is first how to build the hardware, how to build the anchor. Again, even though it's not the topic of my talk, it's something that we call the hardware assistance solution itself. Why? Because in order to build such a secure anchor, we cannot really put it as a kind of like a software code in the software domain, because then if the attacker can compromise the software, they can also compromise the attester. Because attester is something that we have to trust before we trust the overall protocol. That's why people are always leveraging a small piece of hardware. TPM is definitely a more costly solution. But all these solutions have some limitation. First, they are static. Static means that they are vulnerable to TOC, TOU attack, talk-to attack. So which means that when you're trying to verify the device, then they may switch them back into a normal mode. When they try and running by themselves, they may switch to the malicious mode, right? Because it's static, we can only test no matter how frequently we test it. There are always some interval, because if we keep on testing it, then the device cannot really run, right? Now the question becomes, can we come up with solutions that is dynamic? It's a runtime attestation. So let's take a look at the TOC, TOU. So for these memory blocks, so if it's for the static attestation, so it will run it, and it will give a a value, and after you test it, the attacker may compromise some blocks. And if you keep on executing it, you're executing the malicious code. The next time you're trying to run attestation, the attacker would kind of recover back. How to do that? A simple solution is assuming that the attacker can put another piece of memory there with malicious code. So they put the malicious application in the malicious memory, and because they have the physical access, they may maliciously modify the memory controller. So whenever a challenge comes, the memory control will lead the hardware anchor to the benign memory and return the authenticated report, right? But after that, during execution, the memory control will kind of point into the malicious memory section. And in this way, the static attestation solution cannot really identify it. So now the question becomes, if we want to detect this kind of powerful attack, we need to make sure that we verify or we attest it constantly. But if we attest it constantly, then the device cannot work. So now the question becomes how we attest it constantly, but the device still working. So this is something we call the runtime attestation. So the runtime attestation means that while you are running in parallel, we are keep on hashing the status, and then we deliver the data constantly or compare the hashed data with the measurement. So one of the solution is instead of store this just memory hash value, we store the entire control flow graph. So on the left side, we see that if we store the whole control flow graph of the application, so then what happened is, well, we send the challenge and the attestation and the execution is running in parallel, which means that while you execute the code, at the same time, it keep on hashing all the execution paths. For example, we have the PX and the P2. So then we hash the PX path and we hash the P2 path and send them back. And we know that if the PX and P2 compared with the original control flow graph, the PX version is not exist in the database, while the P2 version exists. So we know that this application has been compromised because one of the jump does not exist. So with this, the idea is simple. Now the challenging is how we can make that happen, because now we need to have something in parallel with the processor to always extract all the instruction and run the hash. So, but before we dig deep, now this time, instead of just like we showed you earlier that run the whole static analysis, what we do is that we do the attestation and execution at the same time. So we are reporting the hash value of all the basic block as well as the jump of this basic block. So in this way, we can achieve that first, this the memory bank attack does not work, and this is the hardware assistance scheme. And we also, as I mentioned earlier, now with RISC-V core, it's become much easier for researchers like us to quickly validate the value in the processor, which we can easily download from some open source database. So now we look into the detail. So to the left side of the figure is the original processor pipeline. And we extract the instruction from it, and we go through the instruction filter, because we are only care about the control flow graph. So we only care about the control flow instructions. And there may be some loops So we needed to do some loop encoder to make sure that this loop, we are not really like get into the loop all the time. So it will be endless. And then we do some hash controller and the run hash value. And then we have the hash lookup. The hash value will be compared with the original hash value. This can support both local attestation and remote attestation. For the local attestation, assuming that we have some hash memory, already have data there. For the remote attestation, we can send this hash value to the remote. So this is the overall design, and the hash component is critical, even though all other components are important to make things happen. So regarding the security-wise, the main contribution is resilient to the, we call the memory bank attack and the toggle attacks. So this is something that is a very powerful threat model because we assume the attackers have the physical access or similar to the physical access capability. But it do apply to the IoT situation. And for the performance and area, so we implemented that into the FPGA with around like 15% overhead because we are using the Palpino core with some extra memory. So I just want to kind of pause for a couple seconds here to mention this RISC-V core. As I just mentioned, okay, RISC-V core give the researchers the freedom that now they can really touch a commercial level core and do modifications. And the trend was once looks very promising. Many company or researchers joined in area and they released their RISC-V cores. But if you are really working on this area, you may notice that there seems less and less cores available. Many researcher and the company, they decide to go to commercialize those cores, and they change this open source cores into closed source cores. So I hope this trend will not continue too far, because now we do not really have that many good RISC-V cores. We have a lot of RISC-V cores in the internet, but not that many are very good ones. So, okay, so let's come back. So we have this performance, and some for many of the program benchmark, the overhead is low, but for some of them, they are high, really like those with a lot of jump or cores. The control flow graph is quite complex ones. Okay, so this one is good for RISC-V, but if we really apply to the more popular ARM core, it will not happen because ARM does not allow you to do any modification. Our modification is minimum. We only want to extract the instruction from the pipeline, but it's not allowed. So if we want to apply the similar idea onto ARM core, then do we have any solution with that? So apparently, it seems that not, because ARM does not allow you to do any modification. But from the other side, ARM actually opened another door for us. ARM does not allow us to change the core, but ARM will change the core themselves. For example, that this is our Lahel solution. The Lahel solution is we call the lightweight attestation. We are using the macro cells. What is the macro cell? The ARM core, in order for user to debug it, the ARM core have a very sophisticated debugging capability, peripherals available. And one of the very kind of like important one is the core site debug architecture. The core site debug architecture is almost available in most in all ARM cores, and they can help extract a lot of instruction to help you debug the system. And remember that previously we mentioned what we need is only to extract some instruction from the pipeline. And if we can leverage the core side debugging architecture to extract the instruction for us, why bother changing the course? We don't need to change the course. So this is the key idea of the Lahel. So core side, it turned out, is a very complex system. They have a lot of components. They have trace sources. They have trace link. They have trace sync. They have a lot of them. And in different ARM cores, when I say ARM core, I mean the commercial core from company like TI, like other company like Samsung. They have a lot of, they are not really equipped all of them, but the basic ones like ETM, they are equipped with this. So for the source one, we have the PTM, ITM, FTM. For the links, we have the core side trace funnel, we have replicator. For the syncs, we have ETB, we have TBIU. So not every core have all of them, but PTM, ETB is something quite popular, and which will help us to extract the traces. So for the Zinc 7000, they also have the ARM core embedded in this iSilence FPGA, and they also have the core side components available. They have the ETB, they have the TPIU, and they also have a replicator funnel. They for this component, they almost have the full set. And what we do is we leverage those information, right? So what we do is first we receive and decode the TPIU traces, check the control flow, and then we using the capture the trace to issue this AMBA AXI read request, and the SCU would request from the level 2 cache, and if the level 2 cache missed, we will get the instruction from through the DDR controller. So this is the high level Lahel. So eventually this is more detailed. The left side is the original processing system, and the right side is we leveraging the FPGA reprogrammable logic to program our control system, the trace decoder. So eventually the key idea is that we are leveraging, we attach our component also to the AMBA bus, and we leveraging the core side debugging to get the TPIO traces. And we also using the Snoop control unit to extract all the instructions. So now we have the control flow trace, and we have other instructions. And what we do is similar to the Atrium, we can run the attestation to make sure that the system is running in the benign status. So we have the kind of like testing or some of the benchmark, and we have around like a few percent overhead, and this we don't really need to change the ARM core itself. We just leverage the debug functionality to extract the function for us. So with that said, I want to summarize my talk. Let me check. Yes, I think I kind of like spend more 40-ish minutes. So I want to say the trends. So first, from my talk, I mentioned that from Hafix is ISA modification. Then Atrium is microarchitecture enhancement. Lahel is SoC IP core integration. So these are all hardware assistance solutions. Going further, if we think this path is promising, then what will be the next step? People are talking about even more ambitious, like patchable hardware, like over the air for hardware. The DARPA even have a program called a DARPA reconfiguration security. So hardware was once being treated as a fixed component. Now they're asking the question is whether hardware can be more flexible, because hardware features can support software feature to achieve better security. So with that said, I conclude my talk. Thank you for attending my talk. I know many of you, including myself, are very busy with the deck submissions this year. But I still see quite a few of you attending the talk, and this talk is recorded. For those who did not attend the talk, you may just watch the video. I saw a few questions here. Let me just, Mahedi, let me just read the question and answer one by one.
Sure. Let's do that. And I think if you repeat the question, that would be good as well.
Okay. So the first one called, would the CFG, the control flow graph, be too large for the measurement database, which can be installed in the IoT device? So yes, the very simple answer is yes. But since we are using the hash table, right, we would only collecting the path, and we are store their hash value. So if the value, this hash value is itself relatively small size, even though the control flow graph become very complex, we are storing all these paths. If there are too many paths, maybe the storage on the local IoT device will be an issue. But thinking this way, the storage even for IoT device is large these days, because the storage is much cheaper these days. A few gigabytes for thinking about cell phone or thinking about a small IoT device. They always equipped with like a gigabyte size of the disk or flash, making it possible for storage. Because even though some IoT devices only need a few megabytes, it's these days buying the memory or the flash with a few memory, you cannot even find it from the market. So the same price, you can buy a lot larger size. Okay, I hope I answered this question. So the second question is, would the memory subsystem still be untrusted if it is an embedded DRAM in the SoC? So the okay, I kind of like miss the context here. Are you talking about? I assume that you are talking about the Atrium or the Lahel. We do not really touch this. I see. Okay, I think I understand the question. So if the memory subsystem, which we store the hashed value, is being compromised, that's true. In our threat model, actually, I have something here. I assume that it's about the Atrium one. We have the hash memory here. This is within our trusted boundary. So we assume that we have some other method to ensure the integrity. But if we change the value, then what happens would be we need to make all the time that matching the change the instruction flow along with the hashed value stored there. So for an even more powerful attacker, and if this memory is not within the trusted boundary, yes, it could be some issue. But this is kind of like out of the threat model that we are considering. You are welcome to have further discussion with us to see if we can include the memory subsystem into the not into the kind of threat model, and to see if we can come up with even better solution. Because in this way, people can even thinking about, even though you are not stored local, you are kind of like communicate, then would the communication being changed, then people would mapping the hashed value and with the kind of like an attacker control everything, would that still be possible? It's possible because then it would be too powerful an attack model. We need to come up with even more powerful solutions. Can you compare this between modified and unmodified risk framework? Okay, now I totally get lost. I don't know when you say this means. Okay, maybe I can go to next. We can discuss that later. For the Lahel block diagram, how is the meta memory implemented? DRAM. Oh, let's take a look at the. So we are using the block RAM here. Because the right side of this is in our experimentation is implemented in the FPGA. So we are using the block memory from the FPGA as the resource. CAM is also possible. In fact, if we are using CAM, it will be much faster to check the data to make sure that the data is there, but not in this case. Okay, so what do you mean by over-the-air hardware? So yes, this is a topic. Actually, I saw that the first time I saw that is a couple of years ago, but I don't really saw that much recently. The idea is that we have the over-the-air. Okay, let me repeat the question. The question is that what do you mean by over-the-air hardware? So the over-the-air is always the firmware or software updating, right? So there are some discussions saying that they have some hardware capability, but it's not enabled, right? They have a backup. Over the air, they can triggering those hardware functionality. So make sure the hardware is become visible, become available. We are already using something like this. For example, our memory. When you buy a 64 or 16-bit gigabyte memory, each block is 1 gig or 256 megabyte. It's not just 256, it's way more than that. Why? Because there are always some errors. And the fabrication, they know that the fabrication foundry, they know that there will be errors in the memory, given the density of the memory. So they always have backup plan. They have extra rows there. So when they notice that some line have some error, they would mapping this to the some extra line. So when they mapping this to the extra line, they change the reprogram the controller so that it will jump there. So this is a very simple example or something already widely used over the air hardware. But I do not really see many from this direction. This is a good question. So if someone have more example, we may look into that. Does reconfiguration security allow parameterized trade-offs between security and the performance and the power? So this is I like this question a lot. So when we're dealing with cybersecurity or security, we are always asking the question is metric. So which means that the parameterized trade-off is a dream of every security, not just hardware security researcher, but also software, cyber. We are a network security. That we are always asking that whether it will be a ratio, a metric, or a quantitative value. The reconfigurable solution definitely can help moving towards that side. And it could be something that people would later come up with a table that, okay, if you want to achieve this level, but on the left side, on the right side, that, okay, we have the performance overhead 1%, 2%. But on the left side, it's hard to say that our security improved by 1%, 2%. What we can do, in fact, we are doing, and many other researchers are doing, is we make a table of all these threat models. And we can say that we cover more threat models. If you cover one more threat model, then you will decrease by 1% or 2% based on different type of threat model you are considering. So this, we think is possible. In fact, we have a lot of work. We can have more discussion if you are interested. Oh, we have a very long question. It seems these hardware-based solutions are all of high overhead. Would this be a bottleneck that hinders the practical utilization of these solutions? Also, would modifying the design flow or architecture of processors be the only potential solution, as you said? Some of the existing architecture cannot be modified, yet they cannot be used this solution at all. You are absolutely correct. If we cannot change the hardware, then our hardware assistant solution will not work. And our hardware assistant solution can be divided into change the instruction set architecture or adding more hardware component. So some of the existing architecture cannot be changed. That's true if you are talking about the instruction set. But if you are thinking about SoC, it's different. These days, almost every processor core is an SoC. Adding IP core become much easier these days and much more popular, right? So a lot of solutions, they are leveraging the IP core for security assurance or protection. That's become actually more popular. So this is something that. And when you mentioned that it's the hardware-based solution have a high overhead, I'm not quite sure what do you mean high overhead, because we believe that if you're thinking that adding one instruction is a very high overhead, then yes. But if you are thinking that it's only to not the effort, but the performance overhead, it's no, because adding this instruction does not really change the performance that much, right? But it do require you to know hardware and software. So if you are thinking about knowledge-wise, yes, it's high overhead. That's why the dominating solution is still software, even though hardware assistant solution become more and more popular. There was a picture with memory subsystem that was untrusted. Yes, okay, I know what you mean. So we can discuss that, yes. So the hashed memory and the memory control is something we separated them. Does the, oh, Junfen Fan, hi, hello. Does the CFI hardware enhancement comes with security measurement or even security proof? CFI hardware enhancement, which one you are talking about? The I assume it's the Hafix one. Yes, so we have the security measurement, because if we are talking about the CFI integrity, we have the measurement regarding how many gadgets you can leverage. So this is one of the metric. There are definitely something else. So they would asking the key question that how many gadgets you can still leverage and how many of them you cannot leverage, right? So the reduction of that value is the security measurement for most of the case. Regarding the security proof, I do not really see that if we can give a very like a formal proof regarding the security. Is there any way to get the recording of the seminar? Oh, I'm just to go to the IEEE CEDA website, because these talks are all recorded by the IEEE CEDA website. By IEEE CEDA, they have a series of events. They all recorded. It's on YouTube, so you know how to watch them. Can control flow graph modify dynamically? Oh, that's a very interesting question. So when we're dealing with the control flow graph, we are considering the case that we get the software program and we can do first the static analysis to extract the control flow graph, which means that you already have the code. The control flow graph will not be modified dynamically. If it is modified, which means that you are changing the code. You are changing the legitimate code dynamically. This is not something we consider. We consider that the code is legitimate and we already know that this is this part of the code. Oh yeah, Jinfen said Hafix. Yes, I think I answered the question, the last one. We have one more here. So for a table-based comparison of threat models, do we assume that all of the risks are the same? A very good question. No, we do not assume that. But if we rank them, it's possible. But if we grading them, then people may not agree with each other. Whether this one is more serious than the other one, you cannot this one 0.3, that one 0.1, why 3 times more? Then people will be fighting, arguing all the time. But the table-based ranking system is something that I think we are pursuing, and a lot of groups are also pursuing, even though building such table is a very time-consuming tasks. But we cannot really find anything else with more like quantitative or much easier to compare with each other. So we have some paper that if to discuss that, we can discuss offline if you are interested in this area. And for hardware, kind of like this, the vulnerability could be also software vulnerability, hardware vulnerability. So the table can also be divided into different categories and based on all different threat models. So this is eventually a larger scale or task, but when you are dealing with some specific area, it's easy to kind of like working on that table in that specific area. Oh, well, when answering this question, I have another one jump in saying that if possible, can you and Professor Kari at NYU, Professor JV at TAMU, Professor Kosanfa from UCSC propose a table that we all follow with severity. We will cite all your table paper or have a graph-based visualization. That's a very good point. I need to talk to them. I think among us, it will be a fight to decide which table we go first. But I think each of us already have some initial work to propose such tables. And also, I would encourage you to take a look at some competition. In hardware domain, they have Hack and Deck. The software domain, they have a lot of like CTF. And also the another good resource in the CWE, the database. They have a list of vulnerabilities. And this is a very good reference. Okay, I think I answered all the questions, and these are all very good questions, and I'm very happy that, which means that you are listening to my talk and you are thinking. So I really appreciate that.
So thank you very much for taking so much time to answer all the questions in lots of detail. So there were so many questions, and you take them with lots of care and attention. So it was a very long and lively Q&A session. So thank you again for your very interesting talk. And of course, as you said, with the amount of question, it was proven that, it was something interesting and the audience could follow and enjoy this. So with this, I would like to finish this session. I thank everyone for attending this, virtual lecture series that, somehow popped up from the COVID situation. I hope that we can continue to go back to the normal and in-person kind of sessions. This video, along with all other videos of the virtual lecture series, are available on CEDA website for download. So then with that is, I wish you all the best and hope to see you in the next occasion. So thank you and bye.
Thanks. Good luck with your deck submissions.